Hi 111. In this video we're going to talk about section 3.1, which is discussing something we've already sort of thought about before, which is how to graph lines and what some of their characteristics are, but now we're going to think of them in a new way as functions. So just a reminder that if you feel like you might need a refresher on how to graph lines, there is a section in our textbook that you can review. This is section 1.4, right? So if you need to review how to graph lines, please go to section 1.4, and I've given you some review problems for that on Moodle also already. Okay, so let's go ahead and just jump into this section here. So remember that we have an equation of a line, right? And notice I have our digital textbook open here on the left side, so I'm going to reference us through this section. This is again 3.1. So remember that we've defined the equation of a line in its slope-intercept form, right, as y equals mx plus b, right? And we know what these letters represent, hopefully. Remember that x is considered our independent variable and y is dependent variable. I can use those words now that we've developed them in this class. M is, remember, the slope, and b is our y-intercept. Okay, and usually we've written it like this y equals mx plus b form, right? But now what we can actually do is say, well, it's not just an equation of a line, it's actually considered a function, right? Because notice that if I plug in an x, I will get one specific output, right? So plugging in an x results in one special output. So what that means is we have a function, and so we call it a linear function, right? Linear for the word line. And so here's a definition in your textbook. This is on page 126, if you'd like to find that. And there's the page number right up here in the right corner here, right? That's the page number. So here we have a linear function, and it just looks like this. It still looks like mx plus b. Remember, we've just said that the y, the output here, is going to be determined by this function, right? It's going to be the input is x, the output is going to be y equals f of x, right? It's going to be determined by this rule, mx plus b. Okay? And so here's a little blurb about what this thing's going to look like, right? Of course, because this is the graph of a line, it's going to be a line with a certain slope and y-intercept, just like we did before, right? It's the same equation, okay? So it's going to be slope is m, y-intercept is b, and now we need to think about its domain and its range, of course, because now we're talking about a function, right? So we need to be sophisticated here. So what are we allowed to plug in? Well, notice that our input here just gets multiplied by m, and then you add b. Well, you can do that process to any real number you like, so that means that the domain is any real number that you like, right? Put in anything you want here, you just multiply by m and then add b. Okay, so our domain is the set of all real numbers. Okay, it gets a little bit tricky here when we have to think about the range, and I'll do a little sketch to show you why, right? So you may think about, a linear equation as something that looks maybe like this, right? Okay, I'm not going to give it an equation or anything like that, but in general, that's probably what we think about when we have a linear equation. Okay. When you think about the range for this thing, notice that, if you either do the shading thing or that pencil technique we've talked about in class, or you just think about the y values that this thing is going to produce, right? Notice that the y values that it makes, because the line just keeps going in each direction, right? It sort of gives all of these y values here as well as all of these y values here, right? And it just keeps going and going and going. The whole y-axis would be shaded, or you would touch the whole y-axis if you did that pencil technique here, right? Okay, so what that means here is that in this case, we have said that the range is all real numbers. But notice that the line that I have drawn is a special kind of a line, right? This line has a non-zero slope, right? It has a positive slope in this case, right? But something a little bit funny happens if you, so in this case here, I guess I should say the slope here is not zero, right? But something a little bit funny happens if you actually think about a line which does have slope zero, right? A slope zero line looks like this, right? It goes straight across. It's a horizontal line, right? Okay. And if we think about the range of this thing instead, what does it do? Well, think about it. What are the y values this thing gives out? Does it give out any down here? No, no, no. It only gives out that y value right there. Only that one, right? Because if you think of the shadowing thing or the pencil technique, right, moving up here, the only y value that would actually get shadowed or covered up or hit would be that one, right? Okay, so it only actually has one number here. Okay, so the range in this case is all real numbers. Remember, we can write that with that funny R thing. But here, the range is actually only one number, right? Okay, and we want to say it's one number, a little bit more sophisticated, right? So if we, for example, called the equation of this line something, and I think your textbook right here says, you know, if you give it a slope of 0 here, which is what we're saying, what happens in this equation? If m is 0, that whole first term disappears and you just have what? Or if you think about it here, you would have y equals b, or f of x equals b, right? So if the equation of that line is y equals b, then that means that that equation only ever outputs the number b, right? So in this case, the range would just be the number b. Okay, just one number out. All right, so let's go ahead and just do an example of graphing a linear function, right? Let's do an example. And so again, we get to make use of function notation here. So I'm going to ask us to graph a function, and I'd like to graph, how about f of x equals 5x minus 4. Okay, and we can use any of our graphing line techniques that we have from previous classes. I'm just going to notice that this is in slope-intercept form, and so use that technique. I'm going to locate where the y-intercept is on the y-axis and then make use of the slope to find another point on the line. Then I'll connect the dots. Okay, so let's do that procedure here. Okay, so let's see, y-intercept is -4 right here. Okay, so let's locate that on the y-axis. So let's see, 1, 2, 3, 4. There you go. There's the y-intercept. And then remember, this says right here that my slope is 5. Oops, is 5. Okay, so remember what that means is because it's a whole number, it's really 5 over 1, right? 5 over 1, and we do rise over run to get to the next point, okay? So remember that this 5 over 1 like this can be interpreted as rise over run. And the directions that we rise and run are given by the fact that these are both positive numbers here, right? Okay, so what that means is I'm going to rise 5, so 1, 2, 3, 4, 5 from my starting point here, right? Because the slope says if I start at one point, I can get to another point on the line by following this slope instruction. I rise 5 and I run 1, both in positive directions. Rise 5, run 1. So 1, 2, 3, 4, 5, run 1. There we go. There's my second dot. Okay, arrived at by using the slope. And now we can just connect the dots here, right? And this is going to be tricky with this little writing tablet thing. So get out a ruler if you like to make yours look pretty, but mine I can guarantee you is not going to look pretty. Hey, you know what? That wasn't too bad. That was better than I was expecting. Okay, but notice that this is in fact a function, right? It passes the vertical line test, meaning if you think about passing a vertical line left to right along here, right? When you think of all vertical lines moving left to right, they only ever hit the graph one time, right? So it passes the vertical line test. This is in fact a function. Okay, great. So let's think about some characteristics of linear functions now. I'm going to move to another page in our textbook here. I'm going to skip over to page 129. This is nice with this this digital textbook. We actually get to see the pages here, right? Let me move my thing over a second. Okay, so now let's see if I can just arrow down. Here we go. I lost my little left scroll bar, but that's okay. All right, so one important thing we'd like to talk about in terms of linear functions is whether they are, you know, going uphill, going downhill, or going straight across. We need to use these words increasing, decreasing, or constant that we've developed before to talk about functions, right? And what's nice is that a linear function is always going to be one of the three. It's never going to be, you know, on an interval increasing and then decreasing and or constant somewhere else, right? It's not going to change between the three. It's only ever going to be one of the three, because a line, if you think about it, always does the same thing. It's either always going up, maybe something like this, or it's always going down, something like this, or it's just constant, right? It's always going straight across. Okay, and so in each of these three cases here, we can sort of decide what it is that's determining that the line is doing these actions here, these characteristics here, right? In this one, we would say this is increasing, right? If you move left to right, you'd be walking uphill, right? So this is increasing. In this one, if we move left to right, we would be going downhill, right? So this is decreasing. And this one, we're walking straight across, remember, and we use the word constant for that. Okay. So let's think about what that means in terms of the equation if we had an equation for these things, right? So what makes the difference between these three things in terms of the equation of a linear function here, right? If we think about the characteristics, there's just the slope and there's the y-intercept. Well, remember that the slope is actually what determines whether the line is sort of going up like this or down like this or just straight across, right? Okay, so in this kind of a case here where we've got this like moving uphill, this increasing thing, that's where the slope, remember, is positive, right? That's where the slope's positive. Okay, so if your m number is any positive number, notice I haven't included 0, positive number here, that means your slope is going to be positive, your function is increasing, and it will always be increasing because the line never turns around and does anything else. Okay. Alternatively, when you're heading downhill like this, right, remember that that always happens when your slope is negative. Okay, because again, to get to starting at one point to get to another one, we'd have to go down and then right. Okay, down is a negative movement, right is a positive movement. So in that rise over run, we would get a negative fraction, right? Okay. And here, constant, what happens when we get, how do we get this sort of constant line like this straight across like that? Remember from what we just talked about on the previous page, that happens when your slope is 0. And notice that those three situations there handle all the possibilities for the slope, right? It's either positive, negative, or 0. One of those three has to happen, right? And it will always be the same for the line. For one given line, it will always be constant, always be decreasing, or always be increasing. One of the three. Okay, so we can now use those words in a sophisticated way, right? And we remember we can say that it's increasing, decreasing, or constant over its entire domain, right? Which is, of course, all real numbers. All right, so most importantly for this section is to think about how these linear functions can be used in modeling, in examples, like real life situations. Okay, so let's turn to the examples, or not examples, the problems for this section. I'm going to skip on over to page 135. Okay, and I'm actually going to be talking about this specific example right here, so perfectly lined up. We're going to be talking about number 47. Okay, because there are lots of situations in which a linear function would represent what's going on so that we could model it. So let's read through problem number 47 here, and then we'll do this problem together. So it says the simplest kind of cost function is what's called a linear cost function. Okay, so they're saying a cost function. What that means is that this is a function that tells you the cost, okay, based upon some kind of an input. We don't know what it is yet. Let's keep reading. Okay, they say we have a cost function. They're using function notation here, c, because it's cost, of x. Okay, so x is our input, output is going to be cost. Okay, and it's defined by mx plus b. Okay, we don't know what those letters mean yet. We do know this looks like a linear function, mx plus b, y-intercept and slope, right? And it says where the y-intercept b represents fixed costs of operating a business. Okay, so let's go ahead and write this down, okay? So b is equal to fixed cost. Okay, and if you don't quite know what fixed cost is costs to you that do not change. For if you are producing some sort of an item or a commodity or something like that, right? So, for example, if you had to rent a building to construct your item or your product or whatever, right, that would be a fixed cost because that is not going to change no matter how many items you are going to be building in that building, right? If you're going to be producing 300 items, you're still going to pay the same rent as if you produce 100 items, right? So that's an example of a fixed cost, but there's lots of other kinds of fixed costs. So we can lump them all together in this little letter B. That's what that stands for. Okay, and let's see what else. The slope m represents the cost of each item produced. Okay, so now m here is actually the cost to produce each item. Okay, and so for this kind of costs here, these are sort of like this is like a cost that can change, right? Okay, and this is sort of thinking about things like, okay, well, if I'm going to produce 300 items, I have to think about how much material I need to make those items. I have to think about how many people I have to employ to produce those items. I have to think about how much I'm going to spend on packaging or shipping or transportation, or those are things that depend upon how many items I'm actually going to be producing. Okay, so we've now isolated what m and what b are in terms of their meaning for this problem. And so now let's get into the actual meat of it. We're going to actually suppose that we're running a real business for a second. So it says, suppose that a small bicycle company or manufacturer has fixed costs of $1,800. Okay, so here's our real example. Okay, in our real example that we're making bicycles, right, our fixed costs are $1,800. Well, which letter represented fixed cost again? That was B, right? So in this real example, we're being told that our fixed costs are $1,800, or our B is 1,800. Okay, and then we're told each bicycle costs $90 to manufacture. Well, that we're phrasing there, each bicycle costs $90 to manufacture. That's M, right? Cost to produce each item. So we're being told the cost to produce each item is $90. Okay, those two things together, notice, allow us to write a linear function here, right? We have a slope and we have a y-intercept. Okay, so in part A, when it says write a linear model expressing the cost C of manufacturing X bicycles a day, if we want to go ahead and write that as a function here, I'm going to make use of this function notation. So I'm going to handle part A. C of X, right? The input here is number of bicycles. Okay, because we're told X bicycles in a day, right? X is the number of bicycles. So our input here is how many bikes we're going to make. The output of this function is going to be the cost, right? Okay, so how do I write this? We're told it's going to be a linear model. So we just follow the rule. I write mx plus b. Well, for this bicycle shop, we know that m is 90, right, times x, plus b is 1,800. Okay, and if we just look at this for a second and read it, it says that what? If we want to make X bicycles, then each bicycle costs $90 to make. Okay, so just to manufacture the bicycles, it would cost me 90 times X. Okay, that's just to make the bicycles themselves. Then I have to add to that the fixed costs of $1,800, like the building or any sort of like liability insurance or something silly like that, right? Okay, so this function right here actually does represent the fixed costs plus the costs to manufacture each item, right? For the number of items being manufactured. Okay, so that's for part A. Let's handle part B. It says to graph this model. Okay, let's graph the model. So remember, this is a linear equation. Let's go to the next page here. So we've got C of X equals 90X plus 1,800. Okay, so let's graph this thing. Okay, the y-intercept is 1,800. Okay, so let's go ahead and put that on our y-axis here. I'm going to put it not too high, okay, because again, the scale, I can make the scale whatever I want, right? So that's 1,800. And then it says my slope is 90, right? So that means that to get to the next point, I do what? I go up 90 and over 1. Okay, so let's put that dot here. Okay, and what would that dot be right there? What would the ordered pair for that be, right? Notice this one right here, if I rewrite this for a second. Let me rewrite it as an ordered pair. This y-intercept, remember, would be what? 0, 1,800. Yeah? So now that red dot right there would be what? I have gone up 90, right, for the slope here, up 90. Well, that takes the y value and adds 90 to it. So that means my y value is 1,890. And then I've done what? Up 90 over 1. Okay, so that means if I was at 0 for x, I'm now at 1. Okay, up 90 changes the y value by 90, over 1 changes the y value by 1. Okay, and so to graph these two things, again, we just connect the dots. And again, forgive me if mine, let me try that one more time. That was really bad. There we go, that's a little better. Okay, that's the graph of C of x. Okay, great. So now in part C, it says to actually use this function. It says, what is the cost of manufacturing 14 bicycles in a day? Well, what have they asked us for? What is the cost? Okay, they're asking for an output, right? What is cost is equivalent to saying, what is the output of C of x, okay? But now they're saying when a certain thing happens, right? When we're manufacturing 14 bicycles a day. So what is C of x when x is 14, right? And that would be equivalent again to saying what is the cost here? What is the cost to manufacture 14 bikes? right? That's going to be the same kind of a question. What is the cost to make 14 bikes? That's the same saying what is C of x when x is 14, because C of x outputs our cost to make a certain number of bicycles. So we just plug in 14 into our linear model here, right? So we do 90 times 14 plus 1800. Oops, 1800. There we go. And let me get out my handy little calculator that I have here. So 90 times 14 plus 1800, and you better check me on this. I get 3060. And because this is an application, we better include units, right? Cost uses what? What should we be using here? I see dollar signs all over the place, don't you? So I think this should be dollars. Okay, so in order to make 14 bicycles, it would cost us $3,060, which is what? 1800, which is fixed cost, plus 90 for each bicycle. Okay, and now let's handle part D, so that our video doesn't get too long. Yikes. If you had to take a break during this video, that's okay, I understand. Let's handle part D. How many bicycles could be manufactured for $3,780? Okay, so notice this is like the backwards question of part C, right? In C they said, what is the cost to make a certain number of bicycles? Now they're asking us how many bicycles for a certain cost, right? So they're actually asking us for an x value here in part D, right? So really in part D they're saying, what is x equal to if the cost is $3,780, if cost is $3,780. Okay, well remember that the output of the cost function is cost, right? Okay, so that means we're wondering when does C of x equal 3780, right? Or what value of x do you need to use, or how many bicycles do you need to make so that the cost is 3780? Well, what we can do here is just take our rule of 90x plus 1800 and set that equal to our desired cost, right? Because remember that this rule right here calculates cost when you make X number of bicycles. Okay, so if we want to know when is the cost 3780, well, set the rule that calculates cost equal to 3780. Now let's solve for X. Okay, let's see, I'm going to subtract 1800 from both sides. So let's see, 3780 minus 1800 is, check me on this, 1980. So 90x equals 1980. And now I'm going to divide by 90. And I get x equals negative 42. That would not make any sense, right? X is what? Number of bicycles. You better get a positive number. I was just kidding about the negative 42. I actually got 22. And hopefully you did too. But we can't just write a number here. X has a meaning. It's an application. What was X again? X was, what was X? X was what? Oh, right, X was number of bicycles, so I better write bicycles. So you can make 22 bikes for $3,780. Good to know. All right, in our next video, we'll do 3.2.